Like,
How does quantum mechanics break logic?
we can go over that if you'd like.
All right. Can
Yeah,
you just like
sure.
simplify it? I'm not too familiar with quantum mechanics.
Sure. Yeah, no worries. But I mean, the you'll
Yeah.
have to believe me on some of the statements, but typically the
Okay,
cited
I'll take your word for it.
yeah, that typically the cited theorem is like the number of things that satisfy A and B is always less than or equal to the number of things that satisfy A and C plus the number of things that satisfy B and not C, right? So this is a theorem. It's sometimes called the triangle inequality of propositional logic. It's sometimes called Bell's inequality or the discrete version of Bell's inequality. I typically say the discrete version now because physicists get on my ass and say that's not really Bell's inequality. I'm like, okay, fine. So like normally Bell's inequality is a much more complicated continuous version, but this is just the version that exists in propositional logic, so we like this version. So this is simply a counting argument. It says if I have properties, binary properties, and I have a bunch of things, doesn't matter what things are, and I count them, then this will always happen, right? This is easy theorem, and we can prove it. I can walk through the proof if you'd like. I don't know if you'd like to see the proof or not.
So what do you mean number of like I don't get the inequality.
The inequality, counting the number of things.
Yeah. Number of A and B, what does that mean?
Well, so A is a property, B is a property, and C is a property. So, like for example,
Okay.
let's just do an example, right? We'll go ahead and do
All right.
like, men or something. So here's our objects. Okay, let's pick three properties. What are some three properties about men, right? How about
Hair,
uh,
beard.
yeah, sure, wearing a hat, right? So there's a property. Do you agree that every man is either wearing a hat or not wearing a hat?
Sure, yeah.
Yeah, right, because that's what we
Yeah.
call the law of excluded middle, right? Let's pick
Right.
another property, like I don't know, likes, um, you know, I don't know, Harry Potter or something, right? So, do you agree that every man either likes Harry Potter or does not like Harry Potter?
Yeah.
Yeah, because it's a binary property, right? So, I'm not here like discussing degrees of likeness or something. I'm just saying you fix whatever you want like to mean. Doesn't really matter. Every man either satisfies that or doesn't satisfy that. And then we pick another property like, swims or something, right? Do you agree that every man either swims or doesn't swim?
Mm-hmm.
Yeah, right. And so then we would go down and we'd be like, okay, let's go get a man, right? How about Steve and Bob and, I don't know, Pete, whatever. And then we will figure out their properties. Maybe this guy likes wearing a hat, doesn't like this, likes to swim. Bob doesn't like this, does like this, or likes Harry Potter, does know how to swim. Pete is wearing a hat, likes Harry Potter, and does not know how to swim. Right. So like this is an example. We have any number of things we want. We have any binary properties we want. If you then follow the formula, this will always be true. So if you take two of the properties, we'll call this one A and this one B and this one
Mm-hmm.
C. We then just go through it one at a time. So what are the things that satisfy A and B? So here's A and B. Well, only Pete
Right.
satisfies A and B. So there's just one person that satisfies A and B. So the left hand side is
Right.
1, right? And then we go number of things that satisfy A and C. So we just go down the line of A and C and we see, oh, Steve satisfies A and C. So there's one thing for that category. And then we go A and not C. So not C is
Right.
tricky because it's the opposite of this one. So it's 0, 0, 1. And then we got to look
Mm-hmm.
at B. So we have 0, 0, 1. So, oh, Pete. Pete is both B and not C, but no one else is. So you get another 1 here. And then we
Right.
go, oh, hey, look at that. That's true,
I see.
right? Hey.
Yeah. Okay, that's interesting. Okay.
Mm-hmm. And
Okay, I get it.
that always works. That always works for any things
Right.
and any properties. And in fact, we can prove it, right? Would you like to see the proof?
No, it's fine. I get the idea. It's
Okay.
cool.
So this
Yeah.
theorem is false in quantum mechanics.
Okay.
Now, what does false mean? So in here, in an abstract model, like in propositional logic, right? This thing is derived as a theorem, right? Well, propositional logic and counting. This thing is derived as a theorem, right? And
Mm,
so as a theorem, it is true simply because that's the label that we give things that are theorems of a system. So it's a theorem because it's true because it's a theorem. So technically the word true
mm,
there didn't have any meaning, but as soon as we go to the real world, like this theorem is false in quantum mechanics, we don't mean it's false in a syllogism way because as I just pointed out up here, there is no proof of this being false. There is a proof that this is true. So I can prove this is true, right? And so I would never be able to
mm.
prove that this is false. In fact, it isn't false, right? We can prove it's true, right? So here, when we say the theorem is false, what we mean is that there are experiments that don't comport with this inequality, right? There are
Mm.
um, there are experiments, right? Experiments that don't comport that fail, right? Now those experiments are complicated, but we have a lot of them in different contexts and in different ways. So, in fact, the summary of the fact that this thing is violated leads to the concept that things can be in simultaneity possessing binary properties in at the same time, opposite binary properties at the same time. So in quantum mechanics, Steve could be both wearing a hat and not wearing a hat at the same time. They can be in a superposition of that, right? That doesn't happen at the macro world, and we don't understand how such a thing is even logically possible. But the the quantum world allows that ridiculous notion to be, or appears to do it, and it is because it appears to do it that we are able to actually exploit that and build machines that can actually utilize higher forms of information theory than you can get in a classical system. And so quantum computers are like a testament to the fact that this thing is false in quantum mechanics, right? Because like
Oh,
if
wow,
if this
interesting.
thing was true, quantum information would not yield anything more than classical information. But because this thing is
Mm,
false, quantum computers are possible, and what do you know? We've actually built them, right?
mm,
Wait, so the state of superposition, right? The state
Mm-hmm.
of being something being superimposed, right? What
Superimposed.
how does this disprove that, or not disprove classical logic? That's not what I was gonna say, but how does this show that there's just not some kind of rule that we haven't accounted for?
Well, if there was some, it let's imagine the molecules we're talking about are named Steve, Bob, and Pete. Okay, and then we have three properties here. Okay, this theorem says no matter what ones and zeros you put here, this inequality will still be true. The right side will be bigger than the left side, no matter what ones and zeros you pick. You can pick any ones and zeros you want. Okay. There's only 9 spots here, so there's only 2 to the 9 possible matrices of data here. That's all there is here is 2 to the 9 possibility. So you could literally exhaust. You could exhaust all 2 to the 9, and see that all of them satisfy this 100%, right? And that is what this theorem is. This theorem says if you fill out this table with ones and zeros, you always get this inequality, no matter what you fill out the table with. You always get this inequality. So if you were to tell me, well, maybe we're just misunderstanding something in quantum mechanics, maybe there's just something that we don't know yet, how does that resolve the fact that no matter what you fill this table out with, this inequality is always true? The thing that has to be rejected is that you can't fill out the table, right? That's what has to be rejected.
Right, I think I understand.
Yeah. Yeah, so unfortunately, there's no way to fix it. You're not allowed to know three properties in simultaneity. Quantum mechanics just doesn't allow that. And so the idea of superposition, it's not a superposition doesn't mean we don't know what value it is yet, because otherwise you would be looking at this table where you're just saying, well, I don't know what the ones and zeros are, but I know that they're ones and zeros. Superposition means the thing is literally both values at the same time. It must be, because it can't be binary values. If it was binary values, this inequality wouldn't be violated.
I see. Thank you.
Yeah, of course.